Max Bastian, and I'll be talking about the Week 7 discussion board called the Galloping Gertie, the collapse of the Tacoma Narrow Bridge. And so to start off, we'll be looking at the force motion equation, which is the second derivative of y plus b divided by m times the derivative of y plus k divided by m times y. Now we'll be looking at the variables for this equation, which are b is the damping coefficient, and that has to be greater than or equal to 0. K is the spring constant, and that has to be greater than 0. M is the mass, and that has to be greater than 0. F of t is some artificial forcing function. And now, for part 1, we have to solve the ODE, and before we do that, we have to look at our known values, which are m and k are both equal to 1, and when t is 0, y will also be 0, and when t is 0, the derivative of y will be equal to 2. And now when we plug in m and k into the equation for f of t, we're left with the second derivative of y plus b times the derivative of y plus y. And now I'll be using the undetermined coefficients method in order to solve this ODE. And I'll be using this equation, which is y equals k times e to the RT power plus k times e to the RT power, and y equals e to the RT power, and the derivative of y will equal r times e to the RT power. And the second derivative of y equals r squared times e to the RT power. We'll be plugging these three values back into the equation for f of t, and we're left with r squared times e to the RT power plus b times r times e to the RT power plus e to the RT power, which all equals 0. We're able to take e to the RT power out, and we're just left with r squared plus br plus 1, which equals 0. And now we'll be using the quadratic formula in order to find the value of r, and r equals negative b plus or minus the square root of b squared minus 4, all divided by 2. And now, plugging r back into the equation we'll be using for this method, we'll be left with y equals k times e to the negative b plus or minus the square root of b squared minus 4, all divided by 2, times t, minus k times e to the negative b plus or minus the square root of b squared minus 4, all divided by 2, times t. Now we gotta take the derivative of y, which equals k times the square root of b squared minus 4 minus b, all divided by 2, times e to the square root of b squared minus 4 minus b, all divided by 2, times t, plus k times the square root of b squared minus 4 minus b, all divided by 2, times e to the square root of b squared minus 4 minus b, all divided by 2, times t. We know t equals 0, so e to the t power will equal to be 1. Now we plug in the known value for the derivative of y, which is 2, equals 2k divided by the square root of b squared minus 4 minus b, all divided by 2. And we divide 2 out of the equation to the other side, and we're left with 1. Now we divide k to the other side, and we're left with 1 over k equals b or the square root of b squared minus 4 minus b, all divided by 2. And we get the value k equals 2 divided by the square root of b squared minus 4 minus b. And we plug both k and r back into the equation for this method, and we're left with y of t equals 2 divided by the square root of b squared minus 4 minus b times e to the square root of b squared minus 4 minus b divided by 2 times t power, minus 2 divided by the square root of b squared minus 4 minus b times e to the negative square root of b squared minus 4 minus b divided by 2 times t power. And now when we plug that equation into Desmos, we'll now be left with a graph that looks like this. And so as the slope increases, the bigger the solution becomes, and we know that b must be greater than 2. If b is less than 2, the graph won't exist. and as b increases, the slope of the graph gets flatter. The point value where b looks like it's the closest to a slope value of 1 is when b equals 20, as this graph here. And the units for b are kilograms times meters per second. So now the relationship between alpha and period is that alpha represents the frequency and period is the inverse of alpha. Period also equals the units of time, and frequency is the amount of waves per unit of time. Now we gotta solve the ODE when b equals to 0, and we're left with the second derivative of y plus k times y, and we also treat k as an unknown constant, and so we also use the undetermined coefficients method for this equation, and we'll be using y equals a times sine of alpha t plus b times cosine times alpha t, and then the derivative of y will be equal to alpha times a times cosine alpha t minus alpha times b times sine alpha t, and the second derivative of y will be equal to negative alpha squared times a times sine alpha t minus alpha times b times cosine alpha t, and we're left, and then when we plug this back into the equation, we're left with negative alpha squared times a times sine alpha t minus alpha squared times b times cosine alpha t plus k times a times sine alpha t plus k times b times cosine alpha t, and we know that f of t equals sine of alpha t. And so to make the equation easier, we kind of combine like terms, and we're left with negative alpha squared times a plus k times a times sine of alpha t minus alpha squared times b plus k times b times cosine alpha t, which equals sine of alpha t. And so now we're looking to find the values for a and b, and so we do negative alpha squared times a plus k times a, which equals to 1. And when we solve for a, we're left with 1 divided by negative alpha squared plus k, and we know that b is equal to 0, and so we're left with the particular equation, negative 1 divided by alpha squared plus k times sine alpha t, and this is the steady state solution. And now we got to find the transient state, or transient solution, and for that we'll be using y equals c1 times sine to the square root of k times t plus c2 times cosine to the square root of k times t minus the particular solution, which is 1 divided by alpha squared plus k times sine alpha t, and we take the derivative of that, and we find that the derivative of y equals the square root of k times c1 times cosine to the square root of k times t minus k, the square root of k times c2 times sine the square root of k times t minus alpha divided by alpha squared plus k times cosine the square root of alpha times t. We know that c2 will be equal to 0, and now we plug in the known value for the derivative of y, which is 2. So we get 2 equals the square root of k c1 minus alpha divided by alpha squared plus k. And we found the value for c1, which is 2 plus alpha divided by alpha squared plus k, all divided by the square root of k. And we plug in c1 into the equation, and we get y equals 2 plus alpha divided by alpha squared plus k, all divided by the square root of k times sine times the square root of k times t, and this is the transient solution. And now we combine both the steady state and the transient solution in order to get the equation for y, and y will be equal to 2 plus alpha divided by alpha squared plus k, all divided by the square root of k times sine times the square root of k times t minus 1 divided by alpha squared plus k times sine alpha t. And when we plug that equation into Desmos, we find that the frequencies are with the square root of k and alpha, and when both the frequencies increase, so do both alpha and k increase. And we know both alpha and k cannot be equal to 0, or else we would not have a graph. And some observations as we play with the values for k and alpha. As k gets bigger, the amplitude decreases and the frequency increases, and alpha remains constant for the most part, although if it gets too big, the graph will slowly come to a 0. And now for part 7, as alpha approaches the square root of k, the equation goes from 2 plus alpha divided by alpha squared plus k all divided by the square root of k times sine square root of k times t to 2 divided by the square root of t times sine square root of t times 2. And we plug that equation into Desmos, we're left with this graph down below. And as you can tell, the frequencies are all kind of messy. And when you look at, for part 8, when you compare the graphs between 4 and 7, we observe that 4 had smaller amplitudes and more even ones when k was at the same value, and k equals 3 at this value. In equation 7, the frequency is higher, so this means that a more rapid and continued displacement caused the bridge to collapse.